Okay, then we shall continue on here. So we left off where we just started talking about loops, and so we'll continue our discussion of loops in terms of flow control, and then we'll also start talking about functions, which are very important in our programming. Okay, so I guess before I get back into the loops, though, I just want to mention this one other useful conditional. So we talked about if and else if. There is kind of a built-in function, not a built-in, but there's a compact function called if else, and basically if else the function takes three arguments, which is the condition to test, the result if the condition is true, and the result if the condition is false. Okay, so for example, if you wanted to say is x equal to 5, you could write this, and it tests is x equal to 5. If it is, store yes into n, and if not, store no into n. Okay, and these commands or these lines can be reduced to a single line that says if else x equal 5, yes and no, and then you point the result into n. Okay, so these two things are functionally equivalent. So depending on your usage, you might want to use this. You don't have to. You can use if and else as well. So, but just in case, as you're reading other people's work and other people's programming, you might see this. Okay, and it's not like in terms of computation time. Now that they're like equivalent. Okay. Yes, question.
Is the R equivalent of the ternary operator?
I guess. Okay, let's go back to loops. All right, and so with the loop, you feed it. You start with with the for loop, you start with for, and you say for x or for whatever variable in, and then you give it a vector. Okay, and then so you say for whatever in this vector. And what it's going to do is it's going to repeat everything inside the bracket for each element in the vector. Okay, so you say for x in this vector, then every time what it's going to do is it's going to run through these lines for each element in the vector, and each element in the vector is stored in the value x. So the first time it runs through it, it's going to write 1 squared. Okay, and then it runs it again, and then it goes 2 squared, then 3 squared, all the way up to 10 squared. Okay, so that's simple enough. And then for this command, I think we talked about it briefly. We create a list L, and there are 3 things in L, 1 through 3, and then the letters A through G, and then true and false. And what it's going to do is for each element in this list, okay, so for each element y in list L, it's going to write the length. Okay, and so the result is for the first element, it sees 3 numbers, and then the next thing it sees 7 numbers, and then the last thing it sees 2 numbers. So it prints out 3, 7, 2. Is that cool with everyone? Okay, so it's not going through, because if you think of the list, the list has 3 things in it. So it's not going through each individual item within the list. So it's not doing 1, 2, 3 within the thing. Okay. If you want to store the results from a loop, okay, it's almost always better to kind of define the your object on where you're storing the results. So here I've got res for results, and I'm creating basically just missing characters, 10 of them, because I know my loop is going to have 10 results being stored. Okay, and then so I say for x in 1 through 10, store in results x squared, okay? And what we're saying is that the first time you run it, store the result in results bracket 1, so the first position of results, store 1 squared, and then when it runs through it again, now x is 2, store in the second position of x, 2 squared, okay? Because we're using the subset with bracket notation to indicate the index of the vector where we're storing these things. So after it runs through 1 through 10, we get this result. Okay. Yes?
Will you quickly clarify the replication NA comment then?
Oh, okay, so this just means repeat NA 10 times.
Okay.
That's all. Okay? So when if I run this in R, what it will produce is oops. It's just 10 NAs, okay? And every time I run through it, the first time it replaces the first one, the second time it replaces the second one, okay? So if I ran this loop and I just said 1 through 9 here, 1 through 9, okay? And then I ask for the results, then it does it, we see that it does it for the first 9, and then the 10th one is left NA. These are perfectly valid ways, but in terms of computational efficiency or whatever, it's less preferable, okay? So maybe it's a little too strong to use the word bad here, okay? But so what we're doing here is we're first creating an empty vector, okay? And then what we're doing is we're saying the first time you do it, combine the current empty vector with 1 squared. And then the second time you do it, now you take the results vector, which now has 1 squared in it, and combine it with 2 squared. And then you take that result, and then so you're taking the thing and you're just continuing to add onto the vector. And so you get the same results. It's perfectly fine. It'll work. It is preferable just to say, here, this is what we're going to have, okay? You know, also less preferable is to just start it off with 0, and then you're saying, okay, now in the first position, store x squared, and then in the second position, store x squared. Because every time you're doing this, when it looks at the results vector, you know, the second time it runs through it, it's going to say, oh, you know, the thing results vector only has one item in there. Okay, so the first time you run it, it's no problem. But then the second time you run it, it's going to say, oh, results only has one thing in it, but you're telling me to put something in the second position. So in memory, it has to resize the vector to be length 2, and then it stores it into length 2. And then it runs through it, you know, the third time, and it says, oh, there's only 2 here, but you're telling me to put something in the third position. So it has to resize it to size 3. Now, our computers are so fast that it probably makes minimal difference unless you're working in, you know, millions of items. Then you might see a little degradation in computational efficiency. But just as a good idea, it's kind of good idea to specify where these things are going in the first place. Yeah, we had a question?
What if we do not know the length we're going to have to deal with? For example, it relies on a certain condition, like, I don't know, the number of rows in a matrix.
Yeah, then that's fine. Then you can kind of do this kind of lazy form thing, and R is flexible enough to accommodate that. So yeah, you know what? When you're programming, don't worry about efficiency. General rule of thumb is, as you're programming, don't worry too much about efficiency. Okay, worry more about getting something to do the thing correctly. Once you can get it to do it correctly, then you can start reworking and trying to make things more efficient. Okay? Yes?
If you, let's say you start out by making res and have it like 10 or so like elements.
Yeah.
What happens if, but like in your loop, you don't fill all those 10 elements? Does that produce error or anything?
It won't produce an error. It'll just, you know, if you started off with NAs, so I think I kind of demoed that right here. I said create 10 NAs, but my loop only filled out 9 of them, okay? And so the last element remains an NA right here. So that's the only, I guess that would be the downside to defining all of these spots. It's like, you know, making a reservation for 10 people and then only 7 people show up, you're gonna have 3 empty seats. Is that okay? Maybe, maybe not. You know, whatever. In terms of, you know, it's one thing to, you know, versus the other methods, which would be, that's, you know, you say I'm going to make a reservation for 1 person. Oh, let me call you again. I got to change my reservation to 2 people. Oh, I have a 3rd friend, you know, another person coming. So, and then you have to keep adjusting that, okay? Another question?
What about the other way around? I don't know if you talked about it. So if you make it for like 10 NAs and 11 people show up,
Yeah, then R is flexible enough to just
add it on.
add it on, yeah. You throw it in there, okay? So R is kind of nice. It's like the, I don't want to say the lazy programmer's language, but just, it's very flexible. You don't, it's not so rigid where you have to define a type and then make sure your results that you're going to store in that variable is of that same type, right? We see the coercion where it's like, oh, you gave me some numbers, now you're giving me some letters. Okay, I'll do my best here. Oh, you gave me some letters that had numbers in them and you want them as numbers. I'll do my best, okay? So it does a lot of these things which are nice for you. Okay, which takes off a lot of this, you know, like in C++, you have to really be, you have to say like this is going to be type integer, and you have to make sure all of your results going into that you're storing in that thing is an integer, otherwise it's going to complain. Okay, so that's a for loop where you give it a vector and it goes through each element in the vector. You have alternative loops which run on a condition. So while here says, as long as this condition is true, do the stuff inside the loop. And as soon as this condition is evaluated to be false, then it stops and quits, okay? So the first, you kind of have to start it off with I equal to 1, okay? And then, and it goes in here, and it runs through the loop, and it says, okay, I is 1, 1 is less than 10, so let's run the stuff. And then in the results vector in position 1, store 1 squared. And then we're going to adjust I to be 1 plus 1, 2, okay? And then it reaches the closing bracket here, and it says, okay, now I start at the top of the loop. I'm going to evaluate this thing again. Is 2 less than 10? Yes. And then it runs through the commands. And then so finally it gets to I equal to 10, okay? And then it goes 10, 10 plus 1 is now 11, okay? It reaches here and it goes back to the top, and it says, is 11 less than or equal to 10? Nope. And then so it just skips it and it stops. Okay, so as soon as this is false, then the loop stops. So if you give it something like something that's always true, okay, so for some reason in your code you wrote something and this thing is always going to be evaluated true, it's going to run this loop forever, okay? And so in R, if you give it a loop that if you get stuck in something, you'll see a little stop sign here, and you can break whatever operation it's doing, as long as it's able to. Okay. Sometimes your computer just hangs all of a sudden and says I can't stop. I think Control C or Command C will also do a break if you're in the console to break out of a loop. I should close this. Okay. Is that cool? The while loop? So I think in your homework you'll definitely make use of a while loop. Okay, and then another loop is repeat. Okay, And so with a repeat, it's just going to go into the loop, and it's going to keep running everything in the loop until it reaches this thing break. Okay, so this is like, it's kind of like where the while loop evaluates the condition to see if it should run again. This thing defaults to always running again until a certain condition is met that says quit. Okay, so while is I'm gonna check to make sure the condition is true, and then I'm gonna run the thing. And over with repeat, the default is keep repeating until we reach some condition that tells it to break. Okay, so over here it's the same idea, except now once I is greater than 10, then we better stop. Okay, so we keep running it like this. So here's the same results there. Yes, question?
It's like repeat faster than while, or they're about the same?
There, it's like the same. I actually don't know the true answer to that question, but I imagine it being the same. Yeah, okay.
Is there a particular advantage to using one or the other?
No. Whatever your preference is, okay? Everybody thinks a little bit differently. You know, if I tell you to subtract 37 from 100, inside your brain, you guys are probably doing different operations. As long as you're getting to the right answer, it's okay, right? So, yes?
So, for the for loops, how do you control the increment or decrement?
Yeah, so the for loop, there's no condition to stop it. The for loop doesn't depend on a condition to stop. The for loop, you give it a vector, and it's going to do this loop for each element in the vector, okay?
What I mean is, say, if in a while loop, right?
Uh-huh.
Maybe I can say when I hit certain condition, I want I to decrement by 1.
Okay.
Then keep moving forward.
Okay.
So what about in for loop? Can you do something like that?
Can you?
Let's say we're going from 1 to 10, right?
Yes.
Let's say if I wanna, if at x equals to 8, I hit some certain condition, and I say, okay, now I wanna x go back to 7, and then keep moving to 10. Can you do something like that?
I'm trying to think.
Could you just put in an if statement for that in the for loop?
Yeah, you can put if statements in your for loop. That's no problem. It's just that at the end of the loop, so let's say in the for loop, you say, you know, for you know, you got for, you know, I in 1 through 10, okay? So what this is going to do is it's going to start at 1 and then do whatever is inside these curly braces. And then once it's done that, then it goes on to I equal to 2, and it keeps doing that. I think the question is, once you reach a certain condition, can you have I go back to 7?
Sorry. You know, in C++, you have like I++. And
Right. So you're incrementing. So this notion of incrementing I or something, I think fits better inside a while or a repeat type loop. Because a for, what it does is it just does whatever's inside the curly braces for each element in the vector you supply it. So, you know, once it completes it for I equal to 7, it's going to move on to I equal to 8. And I don't know if there's a way to say, hang on a second, don't move on to the next one, but do something else. Yeah, I feel like that's a bit. It's better off with a while loop or something like that. I'm trying. Yeah, I'll think about it, and if I can think of a better answer than that, I'll let you know. Okay. Oh well, there is a way to skip the current iteration. So yeah, we have keywords breaking next, and so here I've got a for loop, okay, and we're going to start off at 1, and it's going to go through the elements 1 through 10, and what this is going to do is that if I modulo 2, meaning if I is an even number, okay, I modulo 2 equal to 0, is if I is an even number, then break, then quit. Okay, so you can check what is inside the thing that's being processed in the vector that you supplied it. Okay, so it reaches an empty even number, so it says break, and then it stops. Okay. If I do the same thing, but instead of the word break, I put in next, then what it does is once it reaches this statement, it's an even number, then it says next. So then it skips everything below the next, and it goes back to the top of the loop. It goes to the next iteration of the loop. So basically this says print everything, but if it's an even number, skip this printing step and go back to the top. So then it prints out 1, 3, 5, 7, 9. So you can put if statements inside a for loop, okay? But I don't think you can go backwards. You can skip the current iteration with next, okay? Or you can just force it to stop entirely with break. But we have that, okay? Okay, so yeah, talking about for loops, sometimes, so a lot of times you'll see for I in, like 1 through 100, and because you want to do this for the, first 100 times. You want to run the loop 100 times, or something like that. Sometimes you have a list, okay, a list like L, and you want to do it for each thing in the list, okay? Except the value that you want is 1 through 100 or something, okay? So in this case, instead of writing for x in 1 through 3, we can create for x in sequence along L. So you're giving it basically a list L, or a vector L, and it says, so instead of saying to say for 1 through length of L, you can just do sequence along L. And then essentially we're doing the same thing, and we say, okay, well, put in the results in position X, print out the length of the items inside box X, all right? So we're using double bracket notation. What would happen if I put in a single bracket instead of double brackets? What would it print?
Just the length of the. It wouldn't print the item at that.
Yeah, so what it would print would be 111, because it would see, because you're going to ask what's the length of L single box or single bracket X. Then every time you use single bracket, it returns a list of that one thing. Okay, so it's a list with one item. The one item there is 1 through 3, but you're giving a list of 1, so it would print back 111. Okay, and so these are all ways to generate basically 1 through 3 or 1 through however long. You can do 1 colon length of L, sequence along L, sequence the length of length L. Okay, but probably these, if you can't remember a bunch of functions, this one always works too. Okay. All right. Okay, so this is important. The best initial solution is the one you can get working the fastest. Okay, that's just a good rule. So don't worry about optimizing things too early on, because it often forces you to write code that is more difficult to decipher later on. Okay, it is good to keep efficiency in mind, but it's more important to get it right and working correctly and then worry about the efficiency later. Okay, let's talk about functions here. All right, so functions in R have this form, okay? So here we would be creating a function called name colon, parentheses, parentheses, whatever, okay? And in this case, we define it as a function with arguments 1, 2, whatever. And inside the function, we write expressions for it to do, and then we have it return some kind of output, okay? So the function always returns a value. And we supply it these arguments when you call the function. So in this case, we would supply arguments x and y with this command name parentheses x comma y, and then the result of that function would then be whatever's inside the return function here. Okay, so whatever's inside return is what function spits out. Okay. If the function has only one line, the curly braces can be left off. Okay, so generally the function you include everything inside these curly braces, but if there's only one line, you can leave that off. Okay, and if return is not used, it just returns the last expression in the function. Okay, so here this is function f. Essentially, we are just saying take element x and multiply it by itself. Okay, functions are objects in R, so everything in R is an object. All the functions are objects, and they work like anything else. So if we just say if we put this function f inside a list, and we say what is that? It gives us a list with function x. Okay, or a list with a function that's defined as this. Okay, and if you ask what's the type of, it'll say closure, which is even more general than a list per se, if we were talking about object hierarchies. You could return, a function can return a function, okay, which is kind of confusing, but we're defining f2 as a function of x, which essentially, you know, if we're maybe I should parse this into multiple lines here. But you can think of this as curly brace that and curly brace that, right? And then we're closing this off and closing that off. Okay, and so what is function x? Well, inside of that is function y, which is x plus y. And so if we say give me function 1, what it's essentially doing is it's plugging 1 here, but then we could say f2 of 1 and 1, and then it'll process it, and it says 2. Okay, this would be a terrible way to define an addition function, but you could do it this way if you wanted to. Okay. Yeah.
Do we have to use return?
Return is implicit. So if you don't use the word return, then it will return the last line in the function.
I mean, if there is any other words we can use like prints, use prints and it works okay.
You can use print, except it doesn't. So let me just kind of show you. Okay, so here let's just say f2 is we're going to say x times x. We'll call this sq. All right, and then I say print sq. Okay, so we're going to do this. And now I'm going to do f2, 3. Okay, so it prints out. Maybe will this work? I want to just see if. Oh, okay, it still works. It still works. So you can use print. I was afraid that if I used print, it would not actually return the result as the result of the function. But apparently, maybe that's part of what print does. Well, I'm not sure, but yeah, you can use print, which is useful in loops and things like that. I'm just trying to wonder if return is going to get us in trouble. Let me just try something. Okay, so let me just call cube, which is going to be x times x times x. Okay, and we're going to print cube. Okay. So here we go, so I'm defining a function f2, and it should print, so if I do print 3, it should give me 9 and 27, okay? Now, I'm curious what g of f2, 3, what this is. Okay, so in this case, it only stores so it defaults to returning, I guess, the last thing inside the function here. Okay, now we could create something that says return, and I'm going to put in a vector that contains the square and the cube. Okay, so now I'm going to do this. Can you guys see what I'm doing up here? Okay, and then so I'm running this, and now I'm going to try what is f2 of 3, okay? So it does the commands 9 and 27, and then the thing that it returns is this vector 9 and 27. And so if I store the results into G, okay, it runs only the print part, and it doesn't run the return part. But if I ask what is in G, G contains the part that is returned. Okay, so does that distinction make a little bit more sense why we want to use return? Yes, question.
Is there a way to get it so that it doesn't like actually print anything in return, so it's just like
Yeah. Oh, okay, so you just get rid of the print commands here, okay? So if I run this, okay? Okay, and then so now if I do f2 of 3, it does that, and if I say store f2 of 3 into G, it works just like any other function, right?
I mean, if you had something where you just wanted to change x, but you didn't want it to actually show anything, it's just something where you like put in x, and then x changes, but you don't actually, nothing actually pops up at the end if you run the function.
Oh, I'm trying to think. There's probably a way to suppress the output. No, most of the commands you run in R always default to producing some kind of output unless you store the result into something. So usually what you're talking about is like, I want x, let's say x is 3, and I want to modify x to be 3 squared, or x squared, okay? Now if I just did x squared, it's going to default to printing that out. But I think what you have in mind is store x squared into x, okay? And so in that case, yeah, that's fine. And in this case, if I say x is 3, and I wanted to say take the result of f2 and store it into x, we could do that, and then if I print out x, it does that thing, okay? But I'm just trying to think if there are functions in R where it's like you just tell it, f3 of x, and then it modifies x without doing anything and without any kind of assignment. And I don't know the answer to that, because usually if you want the result of a function assigned to something, usually you're doing something like this where you're saying store the result, and then you're giving it the assignment operator. But I don't know if there's something where you just say run the function and modify all this other junk. I'm sure there is a way. There is a way. It's probably less recommended though, because it could be a little little more dangerous. Okay, so, this is what we just talked about. So you can explicitly specify return, and it will return this value. That means whenever you run the function, it returns whatever's in here. And if you don't specify it, then it is implicit. Okay. You know, this brings up a good question. So if I don't specify return, and then so let's say I print, let's say we want to print square here, and then let me just say I'm going to just type in the number 8. Okay, what happens when I run f2 of 3? Okay, so it prints the square, it spits out 8, and if I say give me the result of f2 3, yeah, g actually is the value 8 here. Okay. So so printing works, but it's not necessarily not necessarily the result. And actually here, I have cubed right here, and so I want to see. So that, you got me thinking about all these funny exceptions here. Okay, so it prints out the square. Let me assign the value of f2 to g. Okay, and what is g? Okay, so g is 9. So apparently when you print square, then that I guess it is also implicitly the value of its result there. Okay. Okay, but anyway, all right. So explicit and implicit works out, and then yeah, if you want to return multiple values, you can just create a vector, combine them together, and it will do that. Or you can return a list as well. Okay. Which is often what a lot of the functions in data analysis that you use in R returns things as lists. So when you run the command linear model, LM, and you say y explained by x or whatever, it's returning a list with a bunch of things defined here. Okay, and so your more advanced functions will return things as lists. Okay, and then depending on the operators that you use inside the function. Okay, if you're using just vectorized operators, you can get back vectorized results as well. Okay, so here, over here I said, run f function on the value 2, and it returns back all of these things. Here I'm saying run it on 2, 3, 4, and it returns back vectors in each of these list objects. But yeah, depending on the functions that you use, it might get, if it's expecting only a single value and not a vector of things, it'll complain. Okay. With functions, you can supply argument names. Okay. And so here, the argument names are x, y, and z. Okay. And this is just a really dumb function, okay? It just says, what I want you to do is print out, okay, we're using paste, so it's not really print, it just says, create a character object where you are taking x equal, and then you're pasting whatever this object value is, and then you're going to paste space y equals, and then you're going to paste the value of object y, and then paste z equal, space z equal, and then paste the object in z. So if I say run this function 1, 2, 3, it's going to spit out this character thing. This is just one, a length 1 character vector with x equal to 1, space y equal 2, space z equal 3. Okay. But now that I've defined argument names x, y, and z, I can put these in different orders, z equal 1, x equal 2, y equal 3, and then it will match the argument names with the values inside the function. Okay, and so we get these results this way. Okay, R assumes that things go in the order that they're expecting unless you specify something else. So here I've got y equals 2, and then I don't specify what these are, 1 and 3. So then it just says, okay, well, he specified 2 to be y, and then now, so that one's taken, and I'm just going to take this first one I see here and put it in the first empty spot, and this one, the next one that I see, into the next empty spot. So then I get x equal 1, y equal 2, z equal 3. Okay, so we can do that with argument names. You can also, these are just more examples, okay? So it says, here's this, you've defined this one, you define this one, and then this one is not specified to anywhere, so I'm going to just put it in the one that's not taken, and there we go. And then if you try to use something like m equal to 1, it's going to say, hey, I don't know what to do with this argument here. Okay. You can also assign it default values, right? So you can say here we've got x, y, and z, we've got the same exact function, but if you don't get anything for any of these values, if nobody specifies an x, pretend, give it the default value of 1. So if we don't specify any arguments, then it's going to print out x, y, z equal 1. And then if you give it a 2, it's going to match it to the first argument, and you get this. And then you can also specify, oh, well, I want this one to be this, and then it does that. So it works just like that, but with default values there. Okay, there is something known as scopes within functions, okay? So here we've got function x, and the function x takes x and we're adding y to it, okay? And so what it does is, well, it says if you give it the argument x, it's going to use x right here. But then it says, hey, I'm supposed to add object y. And it says, but I don't know what object y is. Well, it's going to look for it in the higher scope. So inside a function, it's kind of its like own little sandbox that it's playing inside. And it says, well, I don't see y inside here. Let's look into the global environment. Okay, and then it says, oh, well, here's y equal to 1. And then so if we do f of 3, then it takes 3 plus y equal to 1, and it gives back 4. Okay. Here, we've got function x, and then we're going to say, hey, y is equal to 2 inside our sandbox here. And then it'll say, okay, well, you're giving me 3 as x, so I've got 3. And then you want y, and I know y is 2 here. So because it found y inside the sandbox, or inside what's called a scope or environment, it's not going to look outside of that, and then you're going to get 5 here, okay? So sometimes as you're writing functions and things like that, if you keep reusing similar object names, you might realize that things might not behave the way you're expecting it to. It's because perhaps you didn't put the thing that you need inside the scope that it's supposed to be in, so it's looking outside of it and finding something that you weren't expecting to be there. Again, R kind of acts on, it just does the best it can with the information it has. So if it can't find y in here, it's going to try to do its best to carry out the function and look outside. So, okay, so these are some more important rules to keep in mind about scope, okay? Variables defined within a scope only exist in that scope and only for that duration of the scope, okay? So if variables exist with the same name outside of the scope, those are separate and don't interact with the variables inside the scope, nor are they overwritten, okay? So right here I said y equal to 2. This does not override this y equal to 1. This y equal to 2 only exists inside of this function, and as soon as the function is completed, this thing disappears, and there's no trace of it left, okay? If you ask what is y, it's still going to say y equal to 1. So the objects inside a scope don't interact with the things on the outside, okay? So yeah, you can think of a function as its own separate environment that only communicates to the outside world via the values of its arguments and the output expression. Okay? So, for example, if you execute the command rm list equal to ls, which clears out all the objects in the workspace inside a function, which is a bad idea, by the way, you would only delete the objects that have been defined inside the function. Okay? You would not delete anything outside of it. And then the only exception is, I think you guys looked this up in your homework. If you have the double arrow here, okay, then it's going to look outside of the scope and alter values outside of the scope. Okay, it's going to look in higher scope. Yes?
Is this saying that if you have something already existing before your function, and then you try to delete that object in your function, and then at the end of your function, you're not deleting that object?
Yeah, so unless you supply that object as an argument to the function,
Okay.
it's not gonna it's not going to delete the object. Okay.
Just make a copy in your function. And
Yeah. So right, let's say you have y inside your global environment, right? Your workspace, and then inside the function, you didn't ask for the argument y. Okay, and you're working with but the function calls for y, and it doesn't find it inside its sandbox. It looks outside, it finds the object out here, and then brings it in. Okay, and you're working kind of like with a copy of it, and then inside the function you're saying, wait, get rid of this, delete it. Okay, then you're just deleting the thing that's inside that scope. It's not going to interact with the thing out there. Okay, so here's a little example. Okay, so here we're defining x, y, and z equal to 1. Inside the function, we're saying y is 2 and z is 3. Okay, and this is a function inside of this function. Okay, and it says give me back x, y, and z. So inside this function, the innermost one, it only has z equal to 3. It can't find y, so it goes up here and it finds 2. And then it still can't find x, and it goes out here and it finds 1. And then we say, okay, well, print this out. It gives us 6. Okay? But then if I ask R, what is x, y, and z? They're still all valued 1, even though we define them as 2 and 3 inside here. Okay? Over here, though, now I'm using double arrow. Okay? So here, I've got x, y, z equal to 1. I'm saying double arrow y 2 and then z double arrow 3. Okay? Then we ask, what is this? It says it's 6. But then if we ask what is x, y, and z now the double arrows have searched the higher scopes and reassigned those values. Okay? So the double arrow goes into the higher scopes and says, I got you now. Okay? Okay, so I think that covers what we need to know with functions. You should have everything you need to complete this week's homework assignment. Okay, we'll try it out. Do your best. I've got office hours tomorrow. Okay, 5 to 6, and feel free to work with friends inside this class.